Okay, guys, I got the old notes on exponential growth and decay, but I just want to do a new one for you here that goes over our note. So, in particular, this is the growth page. So, somewhere in the 30s in the booklet, and we're looking at a question here where something is tripling. Bacteria is tripling every day. So, on the first day, you have 100, and then it triples every day. So, tripling, doubling, and all that stuff, you can think of them differently. We're not going to be doing half-lives in doubling time. It's a different type of question. But when you look at this question here where it says it triples every day, another way to look at it is to say that it is growing by 300%. Okay, so we're up to 300%. So we'll get to that in a second. And what you're going to do is take a look, make a little chart here. So it's 100, then it's 300, then it triples to 900, then 2700, then 800. Okay, so it's times 3 times 3 times 3 times 3. And you look at the first differences, and they're not the same. You look at the second differences, they're not the same. And what you can do is then look at the ratio here of second differences and realize that they multiply by 3. So if you have a ratio of 3 both times, and if we continue this, it would still be 3, and then you know it's an exponential question. Okay, first differences would make it linear, second differences would make it quadratic, but consistent ratio makes it exponential. And what we want to do is come up with an equation for this, and we can go back to this part of the note a while ago, y equals ab to the x. So if you remember that or not, that is the general equation for exponential um, relationships. And what we have is a couple of parts here, the a and the b, and then the x is the exponent, so we'll leave that for a second. The a is the starting point, okay, so this is the original amount is a. B is your multiple, and then x is going to be your exponent. Now, in this case, let's start with the exponent. We're looking at n is the number of days, so that'll just be n. So that's where we get that n there. And then we want to do the other two parts, and what we say, what we have to find is the original amount for A, and then the multiple for B. And the initial value in this case is 100. Just from the question, it says we started with 100 bacteria, and then you found the rate was 3, and then you just sub that in. So that's it. Okay, so there's your 100, there's your 3, and then you go from there. If you had a word problem where it said something like, and we'll do a couple later, um, and then you can look at the rest of this here. Is it a function? Sure, it passes the vertical line test, blah, 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 blah. And then these questions here, what happens or what are the populations after a week? So that's 7 days. So you throw a 7 in there, get your answer. 14 days, get your answer. But let's do a different question. Let's say instead of growing at by tripling, it's growing at 6%. Okay, so same question, and we start with 100, and now we're growing at 6%. Because it's growing, what we're going to do is add that 6% to 1. Okay, so growth is going to be 1 plus the rate. Decay, which we'll get to in a second, is 1 minus the rate. So the same question, if it was growing at 6%, let's just say I told you that it's growing at 6%. What you're going to do is throw that 1.06 in here. Okay, where you'd see that in a graph is, sorry, let me scroll back up, is, or in a table, is if you got this to be 1, this would be 1.06% or 1.06. Okay, so that is growth. It's growing because the b, or the multiple, is bigger than 1. If it was less than 1, then it would decay. So when we go over here, this next question here, you have a car that decays by 20% per year. The value, or depreciates, not decays, but depreciates, same thing, by 20%. And in this case here, you want to be careful that these questions are a little more difficult because we're not looking at the depreciation rate. We're looking at what remains. So when you do this question here, you're going to multiply by this, the remainder. Okay, not so that's going to be 1 minus the depreciation rate or 1 minus the decay rate. Okay, we talk about decay and depreciation about in a way that we express what's gone, but the questions, when we do the math, we're really concerned with what remains. Okay, so for example, if you say that you're losing 10% per year on something, that's how we talk about it probably. Let's say you have a cottage somewhere and there's a cliff and behind your cottage, and it's decaying and you're losing 10% per year. That's how we talk about it. We wouldn't say this. We wouldn't say it's 90% remains per year. That's a weird way to say it, right? You'd say you're losing 10%. And that's fine. But when you do the math, when we do the calculations, we are concerned with what remains, okay? Because if you look at it, if here's your cliff and that's gone, okay, we don't care about what's gone. Oh, we don't care about what's gone. We care about what's remaining. So next year, we're worried about this white part, and a little more goes away, a little more goes away, a little more goes away, a little more goes away. Okay, so what remains is the important part from a math point of view, but we don't talk that way. So we talk about depreciation, okay, or decay, which is natural, right? Maybe a little negative. Maybe we should talk about what we have instead of what we've lost. Let's think about that for a bit. Okay, that's what I say to my hair every day when I look in the mirror. I'm like, thanks for staying, as opposed to the guys who quit on me. But that's fine. Okay, let's not get into that. Anyway, when you look at this here, what you're going to realize when you multiply this by 0.8 each time, you're going to get smaller and smaller and smaller. And first differences are here, second differences are here, and then the ratio. Now, of course, this is the ratio because we made it the ratio, okay? Because this is 0.8 and 0.8 and 0.8. But when you come up with the equation, same thing here. You're going to start with your initial value, and this here is going to be the ratio here, okay? So you start off with the initial value, in this case was $32,000, and you're going to multiply with 0.8 or 0.80. Don't put 0.20. A lot of people do that. Big mistake. Don't do it. When you graph it, it gets smaller, and then later on, it'll flatten out. And the question is, what happens if it decreases at 15% per year? Well, let's do this question, okay? If it decreases at 15% per year, then that means 85% remains. And if 85% remains, that goes here. Your initial value is still that, and that's that, okay? And then let's do some of the word problems together. Or actually, let's look at this real quick, and then we'll do the word problems. I don't think we need this thing. Okay, this might confuse you a bit, okay? Not the whole thing, but that exponent. We're not going to be doubling time. We're not going to be doing half-lives, okay? But let's do some of these word problems here and figure out what, we're just going to set up these equations. Okay, so we have bacteria and quadruples. So it's growing by 400%. It's 400% larger, okay? So here, if we have a bacteria that's growing, what we're going to do is we're going to come up with this every 3 hours. Okay, so just do me a favor. Just scratch it and put hours, every hour, okay? That's a decent question in 3 hours, but we're not going to get into that. We don't have time for that. Doubling time and half-lives. So even this here, we're not going to get into that much, okay? So here, if I just had 10 milligrams and it quadruples every hour, okay, what you're going to do is, let's say we're going to call this P of T, the population at a certain amount of time. So we'd have to define these things, but we're not going to do that right now. We'll just go with this. We start with 10. That's our initial value. And then you're multiplying by 4. Okay, 4, and T goes there. So it's 400%, which turns into 4. So 10 times 4 to the power of T. If we had this question here that, let's say, instead of quadruples, let's say it grows at 7% every hour, you would go like this, and you would go 1.07. So the key to this is, because it's growing, you're going to add to 1. If it's decreasing, you're going to subtract from 1. So that's your first question. Rare coin is worth 3 times its previous value every 5 years. Again, this question here, I'll show you this question here. I'm not going to hold you to this though, but every 5 years, it triples. So if we let T be time in years, okay, what this question is, and again, you're not gonna have to do this question, but I'll show it to you, is if we start at $10 and you say it triples, you can't put T here, right? Because if we put T there and that's your exponent in years, okay, that's not going to work because it doesn't triple every year. It triples every 5 years. Now you could make T the number of 5-year periods, but that's a bit weird, right? Because if I come back and say, what's the value of this coin in 6 months or 9 months or 22 years, how many 5-year periods are each of those? It gets confusing. So what we do, any idea what we do? What do you think we do here? Any idea? How are we going to change? We're going to change the exponent. And what you do is you make the exponent T divided by 5. So you're not going to have to come up with that. We're not going to do questions like that on the test or the assignment, but those are legit questions that we would probably mess around with a little bit more if we had more time in class. Where the exponent, so the exponent is not just a variable, it's a variable divided by something. Okay, so that we'll do this question here. Number 4 will be a little bit like that too. We'll do number 4, and hopefully this will make a little bit of sense. Let's look at 3. We start at 10,000 bucks, so there's our initial value, and here it's going to appreciate. Appreciate means the opposite of depreciate. It's going to go up, so that's growth. So that'll be 1.45, and then t. So again, don't worry about in this case, don't worry too much about defining the variables and that sort of thing. We're just coming up with the basic equation. Initial value times 1.1 plus the growth rate, 45%, power of t. This one here depreciates every 75% every 3 years. Weird way to look at this question, but if it depreciates by 75%, okay, that means it's going down by 75%. That means what remains is 1 subtract 75%, which is then 25%. You don't have to do the math there, but that's 25% remains. So you're going to have your 50,000, and you'll multiply that by 0.25. Okay, so it's 1 subtract that, the 75, because it's going down. Depreciate means going down. And then you would put time in years here, but because it's every 3 years, again, like question number 2, you're going to divide that by 3. Now, again, I'm not going to hold you to that question. I'd ask you this question. A car depreciates by 75% per year. That's a horrible car to have, but let's say that's the case. What you would do here is you do the same thing, except this would just be t. And this half-life question, let's just look at this question and say, let's change this question. Okay, so let's say we have that, and it decreases by a half every hour. Okay, so that's the question I'll ask you. So there's your initial value, and it decreases by a half. A half-life question is a little bit different, but what we'll do is we'll say if half is gone, half remains. So that's 0.5. So what you do is 1 subtract 5, which is what's gone, and then you end up with 0.5. So that's what 1 subtract 0.5 is, and that will be to the power of t. Okay, this half-life question, a little bit different. Ignore it though. The questions I'm going to ask you are going to be more straightforward, just questions like that. Okay, so you can do a question like this, right? Where you have a town that grows, so it's going to be something like this. Your answer will look like this, 1.10. You're going to add that, and then go from there. This one here, don't do this half-life question. This car is going to increase its value every 8 years. So 15% every 8 years. Not my favorite question, but let's look at this here. 50,000, 1.15. So this is appreciating. So it's an antique car. It's getting worth more, being worth more. Normally, I just ask you per year. You put a T here. But if we have every 8 years, you put T right. On your test, I'm not going to ask you that. I'll just ask you a question like this every year. A motorcycle depreciates every year. Let's just leave it like this every year. These are not the best word questions. If we had a regular class, I would have given you a different package of word questions, but that's fine. We'll go with this. So let's say that it depreciates 35% every year. If 35% is gone, 65% remains. So what you do is 1 subtract 35, 0.35 is 0.65, 15,000. And 0.65 to the t would be that question. And again, let's just go every year here. A diamond bracelet appreciates, and so appreciate means going up again, and 1.28 here. I'm not going to ask you this. I'll ask you a question like, what's it worth in a few years? And then you solve that. And again, more of the same here, not 4 years, every year. What is the value after 3 years? 10,000. It depreciates at 55%, so we're left with that. T, and after 3 years, you just throw a 3 in here. And You can try number 8. It's a bit too much, so I wouldn't bother with that. So that's the way I want you guys to look at the questions in this unit. And